In this section, we want to look at how we can use the definite integral to answer questions about work. And we'll start with a simple question here. How much work does it take to lift a 20-pound weight 10 feet? So I have a little picture drawn with a stick man and a long rope of 10-foot rope with 20 pounds at the end of it. And there's a formula that we typically use when we're trying to find work. It's force times distance. In this case, we have a force of 20 pounds and a distance of 10 feet. And what we get is 200 foot-pounds. Foot-pounds is a measure of work. Now, we might remember that in the metric system, force is measured with newtons, and our work is measured in Newton meters, which is joules. Okay, so we can think about this problem, force times distance, as an integral where the distance changes. Okay, so how could we set up this as an integral, this exact same problem? Well, we could imagine that we have let's say a y-axis here. That's our vertical axis. And at the very bottom, we'll say the bottom is 0. The bottom is a height of 0, and the top is a height of 10. Okay. Then we can think that we're going to integrate the work. We're going to integrate a force. Okay. We're going to integrate a force. In that case, our force is 20. It's a constant force of 20 pounds. And from the distance of y going from 0 to 10. And if we were to solve this integral, what we end up getting is, well, 20y from 0 to 10, which is just 20 times 10, which is exactly what we found. And so this is the spirit of what we're going to be doing in this section. And in earlier problems in like high school physics, you may have used the work equal force times distance formula, but we want to be able to the ability to when the force actually changes. Now let's take a look at some terms and concepts for the section. What are the typical units of work? Well, work, as we saw in the previous example, if we're using pounds and feet, pounds for our force and feet for our distance, then our work will be measured in foot-pounds. And, if you're using units, you just might write foot-pounds. If you're using the standard units for force, that'd be newtons, and standard units for distance is meters. So a Newton meter is the typical units of work there, and that is called a joule. Okay, so those are the standard units of work. The next two questions have us thinking about the difference between mass and weight. Your mass is the same everywhere. If you weigh 80 kilograms on Earth, you weigh 80 kilograms on the moon. Your weight, however, is a measure of force. So the Earth, you'll weigh a certain amount because the force of gravity is pushing down on us. It's not really pushing down on us, but there's that we can think of that force. But on the moon, it will be slightly smaller, right? There is not as much mass on the moon, and therefore there's not as much gravity. There's not as much as a force of gravity. Okay, in the next section, we're making the distinction between measuring the amount of work done on, let's say, a spring, where you have a different amount of force. If you have a variable force by a constant distance, others are set up by multiplying a constant force by a variable distance. So you can measure work in kind of these two different ways. The force changes, or perhaps the distance changes. Okay, let's look at a spring example. So this is Hooke's law. So Hooke's law says that the force is proportional to the distance. So the force changes. It's a linear change. And every spring has sort of this constant of proportion. In this problem, we have a force of 7 newtons stretches a spring from a natural length of 11 centimeters to 21 centimeters. How much work is performed in stretching the spring from a length of 16 centimeters to 21 centimeters? Okay, so there is a couple things that we need to be able to do. We want to integrate the force over the distance in order to find how much work is done. We have to be mindful of the units involved here. Okay, so the units in force, the force units are newtons, right? And it looks like the distance is in centimeters, but that's a problem because in order to get the total amount of work done in standard work is in meters. So we need to change centimeters to meters. Okay, so we have to kind of be mindful of that. Now the nice thing is that it's fairly easy to change centimeters to meters in this case. So in this case, the natural spring, and it's kind of good to draw a little picture just to be able to conceptualize the problem. And we're just going to think about everything in terms of meters. So if its natural length is at 11 centimeters, okay, that's 0.11 meters. Okay, and then it gets stretched to 21 centimeters. So let's try to find the force of this spring. So the force of the spring equals K times X. And the force, now this is the distance, right? The distance that it's been stretched is a total of 10 centimeters, which is 0.1 meters, okay, times 0.1. And that equals a total of 7 newtons. So it took a force of 7 newtons to move it 1/10 of a meter. Okay, so if we solve for K here, K is equal to 70. So that is our spring constant, is 70. So now we're ready to write the corresponding integral for the force, because if we hit the refresh button here, our force is 70x. 70x, okay? So what is the work equal to? The work is equal to the integral, right? And it looks like we're covering a distance from 16 to 21 centimeters. So if we integrate from 0.16 to 0.21, we have a force of 70x dx. And that's it. And that's a fairly easy integral to find. But we had to be able to think about what is the actual force that's being applied to the thing, and we had to make sure that our units line up. Now, if we do this integral 70 over 2x squared from 0.16 to 0.21, what we end up getting here is 0.6475 joules. Okay, so that is how much work it is to move the spring this far. So keep an eye on the units of the problem, and when you're talking about springs, you want to be able to find the spring constant, find the constant of proportionality, given some information about the spring, how far did it, what force did it take it to move what distance. Okay, another application in this section is pumping fluids. So we want to be able to pump fluids, and the only thing different here is that the amount of fluid is the same everywhere, but it's going to take more work to pump fluid at, let's say, the bottom of the tank than it is at the top of the tank. And depending on the fluid, it could be heavier than other fluids. Certainly, like concrete is heavier than water. And some of the weight and mass densities are available in this table here, and you'll see in the applications involving water, if you're using foot and pounds, that 62.4 shows up quite a bit. Okay, and that's just the weight density of water. Okay, so let's look at an example of pumping fluids, and this is a good one. We have a rectangular swimming pool that's 20 foot wide and has 3 foot shallow end and a 6 foot deep end. It has to have its water pumped out at a point 2 feet above the top of the water, as we can see in the picture. And we want to know the amount of work performed in draining the pool. So this is great. So we can just kind of think about a certain slice of water, right, at that point, and talk about how much work is it going to take to move that out of the pool. Then how much work is it going to take to move that out of the pool? How much work is it going to make that out of the pool? And that's where we see the challenge of the problem, is that if we are going to set up an integral to calculate the amount of work here, the amount of work in the top half of the pool is going to be a different integral than the bottom half of the pool, right? We have this kind of natural separation here where the amount of water suddenly changes. Okay, so we need to set up kind of two parts of the problem. We have a top of the pool and we have a bottom of the pool. Okay, and we're going to calculate the amount of work to move the water out of the top of the pool and then calculate the amount of work to take the water out of the bottom of the pool. Now, when I'm doing a picture like this and trying to understand what's going on, it's a 20-foot wide pool, so just kind of setting it up, there's some width to the pool. So we have a width to the pool. Oh, and if we want to kind of think of the pool as a three-dimensional thing, we might want to go like this. Okay, so now we can imagine this 20-foot wide pool. So what is 20 feet? 20 feet is this width here. Okay, and so let's do the top first. The top. And we want to think of, well, how much volume is in the top part of the pool. So the top, we're going to set up a y-axis so that when y is 0, it's the bottom. Okay. Y, this is our y-axis. When we're thinking of y equaling 0 at the bottom, and we're thinking of it equaling 6 at the top of the pool. Okay, so y is our variable that tells us where we are in the pool. And we have to set up that variable so everything will be in terms of that. So if we want to, for y's between 3 and 6, that's what it means to be in the top. Right? Y is between 3 feet and 6 feet in the pool. What is the volume of water that we're dealing with? Well, the volume of water we're dealing with at any one point is we have the cross-sectional area. Okay, so that's we have a 25-foot long pool. That's 20 feet wide. Okay, and that's going to be the rectangular area across the top of the pool. And then a little bit of depth is a change in y. Okay, so y is the variable that we want to integrate with respect to. So we're going to call that dy. So you end up getting 500 dy for an expression involving a really small bit of volume at that level in the pool. So that's great. So that's the volume. And what is the units? I'm going to write units in square brackets, which is kind of common. That's cubic feet. Right? Volume we're thinking about in cubic feet. But this is water. So we also have a weight, right, density of water, which is 62.4. 62.4, and the units for that is pounds per cubic feet. So what do you get when you take, we get the force? What do we do to get the force? In pounds, you take the volume times the density. So volume times density, and that's a common formula. And in our case, we get 62.4 times 500 dy, and you get cubic foot 10 pounds over cubic foot, and we just get pounds. So there's our force, which is awesome. So now we're back to, we just want to be able to integrate the force, right, with respect to the distance. So the work that's done on the top, right, is going to be the integral, and we're going from 3 feet in the pool to 6 feet in the pool of our force. Okay, but we don't have the distance yet. So we want to figure out at what distance is the water. So we have to have it 2 feet above. Okay, so at the top, when y is 6, we want there to be a 2-foot distance. We want to multiply this distance times 2. When we're 3 feet in the pool, it's got to go 5 feet out. So that turns out to be 8 minus y. Now let's think about that, 8 minus y. If y is 6, that means we're at the top of the pool, but even the layer at the top of the pool has to get pumped out 2 feet. And if y is equal to 3, then we're at 5 feet. That means the water has to travel 5 feet out of the pool. So that is going to give us our distance there. Okay, and if we do this integral, we end up getting approximately 327,600 foot-pounds. Right, and remember that is the units that we're dealing with here. This is the feet, and over here we found the pounds, right, in red. So whenever you're setting up these integrals, you really want to make sure that you're getting the units right, because that's definitely how you know you're setting up the integral properly. Now let's look at the bottom of the pool. Now the only thing different about this is the volume isn't some nice rectangular piece. So if we were to think about, if we just take a look at the bottom from the side, it would look something like this, right? It would be 10 feet along the bottom, and then this part where it rises up is 15 feet. And then we go 3 feet here. So y is going from 0. I'll have this be y. Y is going from 0 to 3. From 0 to 3. And so how do you figure out, exactly how much water would be at one of these cross-sectional areas? Well, we need an expression in terms of y of how long that is. And you can use kind of some proportional arguments here. This is just linear growth. It's y, this length, the amount of water here is growing linearly as y increases. So when y equals to 0, the length is equal to 10 feet. And when y is equal to 3, the length is equal to 15 feet. And if we looked at the change in length over the change in y, so change in length over change in y, we get 5/3. So for each 1 unit increase in y, the length increases 5/3. And we can write that down. We can see that the length here, right, in terms of y, would be 10 plus 5/3 y. And let's check. When y is 0, indeed that's 10. The length when y is 3, indeed that's 15. So that is how long this blue part is. This blue part here is 10 plus 5/3 y. And that way, this total volume is varying, but we have an expression in terms of y. And now the rest of it, so let's write the volume down. We have a width of 20, right? A width of 20 feet. And then we have a length here of 10 plus 5/3 y dy. And so a small change in y times that amount of area gives us a little piece of volume at that height in y. Now here y is between 0 and 3. Okay, what about the force? Right, what about the force? The force is equal to the weight density times the volume. And the weight density here is 62.4. Right? Times our volume. So that's times 20 times 10 plus 5/3 y dy. And then our distance, in order that it has to cover in order to get out of the pool, is still going to be 8 minus y. Right? When y is 0, you got to go all 8 feet. When y is 3, you have to go 5 feet. So the work, we're ready to write the work of the bottom. It's the integral of y goes from the bottom to 3 feet of 62.4 times 20 times 10 plus 5/3 y. So that's our, and all of that is our force. And then our distance that we had to cover is 8 minus y. Okay, and when you multiply all that out, it's just a bunch of numbers, and it's a polynomial, relatively easy thing to integrate. And we end up getting 299,520, in this case, foot-pounds. And so the total amount of work is the work from the top plus the work of pumping out of the bottom. And that's going to be you add these two numbers together and you end up getting 627,120 foot-pounds.